Thank you very much for the invitation. You have to click the I accept the button. Okay, so indeed, the subject, this is going to be kind of sort of survey talk. I'm not going to talk too much about recent results. And it's going to be generally on the subject of symplectic resolutions. And well, I recently wrote a survey paper on this topic. So if you're interested, everything I say was in this survey paper, which is on the archive. Okay, so this is symplectic resolutions, is a subject which has been kind of an intense study for about 10, 15 years. And where it started was that representation theorists have been interested for a long time in the geometry of the cotangent bundle of the flag variety. So let me begin there. So start with the flag variety. So flag variety is just the space of all flags in a vector space. The n-dimensional vector space over the complex numbers. That's the flag variety. And then another player is the nilpotent cone. And the nilpotent cone is the space of all nilpotent matrices. By matrices, which are nilpotent. And then the cotangent bundle of the flag variety emits a nice description using these nilpotent matrices. You can say that the cotangent bundle of the flag variety is the space of pairs of a nilpotent matrix and a flag, where the flag and the nilpotent matrix are related with the matrix that takes you down step in the flag. Classic picture of this is when n equals 2, then our there's a morphism, obviously, from here to here. So here's a nilpotent cone where n equals 2. So we have 2 by 2 nilpotent matrices. So such a matrix must have determinant 0 and trace 0. So the entries of the matrix look like so. And the determinant 0 condition is that uv plus w squared is 0. And this is, well, up to maybe like throwing in some I or something. This is the graph of the real solutions to uv plus w squared equals 0. And so we have a map. I guess we should. There's an obvious map here from the cotangent bundle of flag variety to the nilpotent cone. N is 2. So the flag variety is just P1. And so I'll think of it as a circle. Real locus would just be a circle. So the cotangent bundle of flag variety looks like some kind of cylinder. And that's not like a sort of nuclear power plant picture. And the morphism from this cotangent bundle of the flag variety, well, cotangent bundle of P1 in this case, is basically is an isomorphism everywhere except it collapses the 0 section on here to the singular point of this cone. Cotangent bundle of flag variety. Okay, so this is the picture when it is 2 and more general situation. So what are the features of this cotangent bundle of flag variety? Push it up, I guess maybe online audiences. That's the switch. So what are the features that we see? Well, this cotangent bundle of the flag variety, like any cotangent bundle, carries a symplectic structure. And whenever I say symplectic in this talk, I'm always going to mean algebraic symplectic structure. So symplectic structure is a category of algebraic varieties, or you could say holomorphic symplectic structure. So the cotangent bundle of the flag variety is symplectic, and the map from the cotangent bundle of the flag variety to the nilpotent cone is a resolution of singularities. Okay.
It's a little bit hard to hear you.
Sure. Okay, the map from the cotangent bundle of the flag variety, cotangent bundle of the flag variety to the nilpotent cone is a resolution of singularities. So this is the sort of thing that we're going to generalize. So our definition is a symplectic resolution is the following. We have two spaces, y and x, and a map between them. And y is a smooth algebraic variety and carries a symplectic structure. And x is a affine. It carries a Poisson structure. Let me again emphasize the last time I always made algebraic symplectic structure. So from the differential geometry viewpoint, I know most of the audience of differential geometers maybe. From the differential geometry viewpoint, would be, well, usually this y would carry a hyperkähler structure. So I'm not going to speak about that today. So that's x and y. And the map between them is a resolution of singularities, which means it's projective, birational, so it's one-to-one on an open locus, an isomorphism on an open locus, and also a map respects the symplectic and Poisson structure, so it's a Poisson morphism. Any question about the definition?
Can you remind us what Poisson is?
So Poisson means there's two approaches. One, you could say it has this Poisson bivector, or maybe simpler, more algebraic, at least simpler for me, is that if we take the coordinate ring of x, so the ring of algebraic functions on x, this is a Poisson bracket, so it has a Poisson bracket, which means bilinear map. Itself, which is a derivation for the multiplication, and which satisfies the which is a Lie bracket. What do you call it? Jacobi identity, and is the derivation for the multiplication. Any other question?
Is that like a commutator in the case of your
Not exactly. I mean, this is a bracket on the functions, not on the space itself.
Is there like an example that we should have in mind? Because that doesn't say anything to me.
Yeah, for the Poisson bracket, so Poisson bracket you can think of as a kind of degenerate symplectic structure. So in this nilpotent cone here, it's symplectic everywhere away from zero, and at zero here has a trivial symplectic structure. Maybe what I'm about to say in a second will be more helpful. Any other questions? So this symplectic resolution, we're going to be interested in a couple of actions of tori on this thing. So this y to x is called conical. If we are given an action of C star on y and an x, so it acts on both spaces compatibly with this map, which contracts x to a point and scales the symplectic form. So in our example, this action would just be the scaling action on the matrices. So this action would be the scaling action on matrices. In fact, to a point. And then there's another action we're going to be interested in. And so this is called Hamiltonian. Approaching y or x to a point. This, x is the Coulomb, the singular one. Y is this one. Like actually won't do anything on this P1, so it won't contract. This map from y to x is called Hamiltonian if we are given an action, another torus, usually bigger than one dimensional, on y and x. And it should be a Hamiltonian action. So that means it preserves the symplectic structure and has a move map. I won't bother explaining that, but that is not that important. But one important feature is that we want this fixed point set to be finite on y. It only has finitely many fixed points in y. So in this case, the action would come from just the action of the diagonal matrices. So we have the diagonal matrices. We can use the diagonal matrices to act on flags. We can use the diagonal matrices to act on the nilpotent cone. And this action on this cotangent bundle of phi variety has precisely two fixed points. Here are the P1. They correspond to the two flags we would make using the standard basis. Well, a flag in this case is it's just a single line. So the two lines we make using the two standard basis vectors. And if you like picture the action, you might picture the action something like this. That's this torus. Here, picture of the action.
YT again is the
Fixed point set.
Torus assumed to have the same real dimension as, like, is the dimension of the torus important?
No, typically it'd be smaller. When a variety who's within, in fact, the biggest this torus can be is half the dimension of y. Actually, that case is very important. It's called this hypertoric case. So that's the biggest thing. Like in this, I mean, well, it looks like this torus is actually two-dimensional and this space is two-dimensional. But despite the fact that this torus is like this, actually the diagonal matrices, the multiples of the identity matrix, they all act trivially in this action. Anything like this actually acts trivially because it's acting by conjugation on the matrices and by acting on this subspaces. So it's actually not really this thing. It's really T mod C star times the identity matrix. So it's actually in this case only one dimensional. Okay, so what are some examples of these symplectic resolutions? So as I mentioned before, one example is this cotangent bundle of the phi variety. Oh, thank you. And more generally, we can do a cotangent bundle of G mod P, a partial phi variety, where G is any semi-simple group with complex numbers. And P is any parabolic subgroup. For example, cotangent bundle of a projective space or cotangent bundle of a Grassmannian. In fact, there's some conjecture, which I think is still open, which is that a cotangent bundle is a symplectic resolution if and only if it's a cotangent bundle of a partial phi variety. But there's not very many examples of these symplectic resolutions. That's what makes them attractive to study, at least for. With me. Okay, another example is if you take gamma inside of SL2C, a finite subgroup. Classified by the multi correspondence. Then form the quotient of C2 by that gamma, and because it's in SL2, which coincides with the that means it preserves the standard symplectic structure on C2. This thing will be Poisson, and it has a resolution called that's like sort of a unique resolution. It's called the C2 mod gamma is called a Klinean Singularity. This guy is called the resolution of Klinean Singularity. So this is my X, this is my Y. In this example, this was my Y, and X would be some family of no-voted elements of the Lie algebra. So besides these examples, there's a kind of somewhat general procedure for constructing them. General procedure uses what's called Hamiltonian reduction. So I begin with G, any reductive group. So the examples you should have in mind is GLN, or maybe some product of GLNs. Groups of invariant matrices. And N is some representation of G. Vector space with an action of G.
Joel, could you flip the camera?
Oh, sorry.
Thanks.
All right. And then we form the cotangent bundle of N, which is just the same as N direct sum N dual. Carries a symplectic structure and has a moment map I to D dual. And then we form the Hamiltonian, we find Y to be the Hamiltonian reduction of T star N by the action of G, which means we form phi inverse of 0. And then we take a quotient by the action of G. And I'm going to put two lines to indicate that we take a kind of projective GIT quotient. It's not too important what this means exactly, but we take a quotient of this 0 level of the moment by the action of G, and it's called the Hamiltonian reduction, and Y carries usually a symplectic structure, and sometimes this gives a symplectic resolution. Not usually, but sometimes this is a symplectic resolution. And there's two special cases of this general construction which are very useful. One is when G is a torus. And in this case, Y, the thing you get from this symplectic reduction, is called hypertoric variety. So these guys are very good to study because when you work with tori and representation of tori, everything is very simple and combinatorial. So these things can be studied combinatorially. So they're closely related to toric varieties. In fact, they're built out of, they're sort of like a cotangent bundle of a toric variety, although not exactly. But they're closely related to toric varieties. The second important special case is when G and N come from a quiver. In this case, Y is called a quiver variety. So maybe it's not obvious what I mean by G and N come from a quiver. So I think I'll come back to this later. Exactly. We'll return later to what these quiver varieties are and what it means to say that G and N come from a quiver.
Sorry, what is X in this picture?
So good question. So there's it comes down to this kind of quotient. So maybe I should explain this a little more clearly. So the most naive quotient you can take here is what's called the affine GIT quotient, which means you take the coordinate ring of phi inverse of 0. So phi inverse of 0 is an affine variety because it just is an affine variety. Just take a level set of morphism. So the simplest thing you could take is take the coordinate ring of phi inverse of 0, and then take the g invariant functions, and then take spec of that. So that thing is called the Affine Ga2 quotient, and that's what x is. And y is this more sophisticated thing where you have to use this chi, which was a character of g, and you take instead the semi-invariance for the chi and take a proj. Right. If you haven't seen it before, it probably won't be that easy. But this x is a kind of naive quotient, and y is a more complicated quotient. Maybe. Okay. Any other questions? I could do this quiver example now, or I could save the quiver example. Save the quiver for later. Let's save the quiver for later. Explain what it is. Okay, so what do we want to study about these symplectic resolutions? Well, one thing we're interested in is the topology of symplectic resolutions. So we have this I from y to x. Let me explain what I mean by topology of what I want to study. So we begin with the theorem due to Klinean, maybe from about 20 years ago. So it says that x has finitely many symplectic leaves. So x is a finite partition. So pieces, and all these xj's are smooth, symplectic, and look like. So this is well, when you ask somebody else, how should I think about this Poisson structure? So maybe this is one answer. So you have this x, and it has some singular things, but these like pieces here, that'll be one of these, maybe x1, one of these symplectic leaves. I mean, it'll be like two to at least even dimensional. So all these pieces are even complex dimensional. So here's x1, and then maybe here's some point x2, and maybe here's the open part x0. So that's the way you should picture these spaces, and each of these are symplectic things which are of smaller dimension, which are put together to make up x.
Form some sort of singular foliation?
Yeah, I mean, overall x is singular, and but these are themselves smooth. But there's only finally many, so I don't know if foliation is right backward.
Okay.
I mean, in general, when you have Poisson manifolds, varieties, they have a foliation by symplectic leaves, but here it's only finite, so it's a very special situation. And the second feature of this topology that I'm going to talk about is that pi is semi-small. So semi-small means the following. It means that if we're going to be interested in the fibers of this map, so we have y mapping here. So we pick some point and we let fj be the fiber over a typical point xj of big xj. Pick a big point in each of these smooth pieces, and I take the fiber, call it fj. And semi-small means that the dimension of the fiber is half, or at most half, dimension, the codimension of the stratum that it's over. I guess it's not quite. So this condition of dimensions is very useful because it allows us to apply what's called the Valence and Bernstein-Deligne decomposition theorem to study the cohomology of Y. Composition. The cohomology of Y decomposes as a direct sum over these strata. I write capital J and write it before. Capital J is just the index set of these little j's, so this finite set of strata. And I get what contributes to this thing is the what's called intersection homology of each of these closures of these strata. Tensor the top homology of the fibers. So intersection homology is a homology theory that's adapted for singular algebraic varieties. But in a few minutes, I'm going to get rid of this intersection homology. So if you don't like it, you don't have to worry too much about it. So again, the picture you should keep in mind. So you have these different strata here, and over each one you have some fibers, and the fibers are getting like this fiber is just going to be a point because generically the map's on isomorphism. Anyway, generically the map's on isomorphism, and the biggest fiber will be over the smallest point here. But one of the strata actually will always be, if you remember, there was the C star action contracting X to a single point. So the smallest stratum is actually that single point. And the biggest stratum is open. So we can further study this piece using this Hamiltonian C star action. So we'll choose a sort of generic choice of C star inside that Hamiltonian torus, and then we'll let X plus tracking set for that C star. All points in X as the limit of action gives you the 0 point. So we have a 0 point inside of X, which is this cone point. And then we're, remember the blue action I drew over there, it's going to contract exactly this part. The other things are going away. This is the X plus. And then we'll similarly let X J plus be just the tracking set inside each stratum. And then a little lemma tells us that this intersection homology can simply be studied using this attracting set. It's just the top homology. So after replacing this intersection homology by the top homology, we reach the following: that the cohomology of Y decomposes as a direct sum over the stratum of the top homology of the tracking set of the stratum tensor the top homology of the fiber. And I should say, what does it mean, this top homology? So typically, these things are going to be reducible algebraic varieties. So this top homology will consist potentially of the more than one dimensional, and will have a basis given by the irreducible components of this variety.
Usually for intersection homology, you have to specify a perversity.
This is all middle perversity, which is kind of related to this issue here. Let's look at some examples of this decomposition. So I mentioned this resolution of Klinean singularity. So let's take the Klinean singularity C2 mod Z mod F. So that'll be my Y. That is all C2 mod And well, what does this guy look like? Well, if n is 2, you just get the same cone that I've been drawing over and over again. And if n is not 2, well, it's close enough to such a cone. But the resolution depends, interestingly, on n. So the resolution sort of looks like I've been kind of drawing it. But over the singular point, instead of just having one P1, you actually have a chain of P1s. So maybe I'll just draw it. So rather than drawing it as a circle, I'll draw it just some little lines. So you actually have n minus 1 P1s sitting over this singular point. So this is the F. I made some horrible mistake here, which is that I should have never numbered them this way. Let me go back to this. We always number it so the singular, this cone point is F0 and the numeric point gets the biggest number. So okay, so here we have two strata, x0, which is the point 0, and the rest of the space, which is just x1. And so our decomposition will go as like so. We'll see the topology of this x1 plus, which is just going to be one-dimensional. Insert the topology of this fiber, which is just a point, and also one-dimensional, plus the topology of x0 plus, which is also just a point. So that's also one-dimensional tensor. The interesting thing, which is the topology of this fiber over 0, which is this n minus 1 p1s. And because we have n minus 1 irreducible components, as the topology has a basis given by those n minus 1 guys, so it has n minus 1. So overall, this way, 1 times 1 plus 1 times n minus 1. That's up to n. Okay, so that's one example. Now another example.
When n equals 2, is it just a bar?
Yeah. I mean, I think for any n, it's a blow, just a blow of the singular point. Just when it's only when the picture is only really correct when n is 2. I don't know how to distinguish the other codes for this one.
But again, in higher dimensions, it's not a case of blowing up points because it's no longer semi-small.
That's true. And moreover, blow-ups are generally not semi-small. Here it is because the dimensions are small. But also another thing which is more complicated in higher dimensions is that the singular locus is not x is not just a single point. It'll be bigger. So here's another example, which is a bit higher dimensional. I'll take the cotangent bundle of Pn minus 1. That's one of my Gmod P's. And it resolves a space of matrices, as I mentioned before, which in this case, it just n by n matrices, which have square 0 and rank at most 1. So very simple space of matrices. Then in this case, we're going to consider the same decomposition. So within the space of matrices, there's again only one singular point, which corresponds to the 0 matrix. It's the 0 matrix. Because that would be the matrix with rank 0. And the rest of the matrices have rank exactly 1, and then they form an orbit under the actual GLN. But in this case, if we run the same, so at first glance, this decomposition looks sort of the same. Two strata. And some things are unchanged, but what happens here, this x1 plus, this is the space of such matrices which are upper triangular. So if you could study the space of upper triangular matrices with rank 1 and square 0, you'll find this space actually has n minus 1 irreducible components. So this first factor here will contribute n minus 1. It's n minus 1 dimensional. This factor is again just a point, so it's just one dimensional. This guy is also just a point, so it's one dimensional. And this F0 is actually just the zero section inside this cotangent bundle. So this Pn minus 1 is precisely what maps to 0. And as you said, it's in this example, it's not exactly that blow up. But this Pn minus 1 is what is the exceptional fiber. It was one mapping to 0 here. But anyway, it has only one irreducible component, so it's 1. Okay. So if we compare these two examples, you can notice that this n minus 1 here has moved, has like migrated from here over to here. Otherwise, everything stayed the same time. Well, that's not, that doesn't sound too exciting, but it turns out this is actually the special case of a very general phenomenon.
You've got something. So 0 here is like the singular point, and fiber F0 is the 0 section of the cotangent bundle.
Exactly.
So doesn't that, what was the semi-small condition that the dimension of the fiber?
Is less
Oh,
than,
I see.
less than half the codimension. So this 0 is half of this.
Oh, right, yeah,
This thing
yeah, I
is
see.
dimension,
That's exactly half.
2 n minus 2 and
Yeah.
dimension n minus 1. Okay, so I was trying to tell you that this funny n minus 1 migrating over here is a very special thing. So observation is that symplectic resolutions come in pairs. So if you have one symplectic resolution, there's another one lurking around. And maybe this one might have indicated the dual of this one is this one over here. So this observation was first made, well, quite a long time ago in physics, maybe in the 90s, by Intriligator, Seiberg, and independently in math. Well, also some time ago, I guess, in math, maybe a little more than 10 years ago, 15 years ago, say, by Braden. And Webster. So in this symplectic duality is a big story, and it's another name for symplectic duality, which I don't know, just sounds nicer, but is 3D mirror symmetry. So many people are familiar with the ordinary notion of mirror symmetry, and that's like 2D mirror symmetry, the usual mirror symmetry, and this one is for some reason called 3D mirror symmetry. We'll see in a few minutes, like something that's 3-dimensional, but not really well.
This has got a first in the 80s.
Sorry?
This Seiberg observed this first in what age? What period?
Oh, when you mean? I think in the 90s. But I'm not very familiar with the physics literature. But I think I mean, at least this paper I think is like 95. But I actually don't know if people knew about it in physics even before that. Okay. So in this symplectic resolution, certain structures on Y they kind of match certain maybe other different structures. So that's very vague. Let me explain one manifestation of this, which we can see as an example of it written here. here's one example. So there is an order reversing bijection. So when say, so this is what one, I mean, when you say I have this symplectic dual pair, it means that I expect certain things to be true. And now I'm telling you one of those things that I expect to be true. So there's an order, so it's not really a theorem, it's more of a thing that one should try to prove in any given example. Okay, so there's an order reversing bijection between J, which was the symplectic leaves of X, and J shriek, which was the leaves of X shriek. So the two guys are called X shriek and J shriek. I mean X shriek and sorry, X and X shriek. Or Y goes to X and Y shriek goes to X. So there's show you order reversing bijection. Order comes from just the closure relation of strata. And I'll write this bijection Y goes to, sorry, J goes to J, little J goes to little J. Such that the topology of X squared plus is isomorphic to the topology of the fiber at J shriek. And vice versa. So what this has the effect is that these two decompositions of the cohomology of Y, the cohomology of Y shriek, are reversed sort of in two ways. So we would have this one, and then it would be isomorphic to the cohomology of Y shriek, but like reversed in the sense that the pieces here get swapped to pieces here. I mean, these pieces come from, we have these pieces like here coming from this strata. So this strata here will correspond to the furthest one to the right here. And the pair, the things you see here will get themselves swapped in here because it exchanges the fiber for the tracking set. So, part, we'll go over to this part. This part, we'll go over to this part, and then so here we see an example. This n-1 ended up here. This one went here, and these two ones got switched with these two ones, but that was harder to notice. Okay, so this is an example of one of these matching structures. Let me just highlight a couple more examples without as much detail. So some other examples of matching structures was, I guess, the last time I spoke in this seminar, it wasn't that long ago. Something like I spoke in the seminar just over 2 years ago. It's one of the last seminar talks every day, and I spoke about the Akita conjecture. That was that's another example of some matching structure. We won't go into detail. Another example, which was a pretty big motivation from the representation theory point of view, is this certain thing called a causal duality between modules or quantizations of these symplectic associations. I won't go into that detail, but maybe a tiny bit more I'll say one thing about is that there's a matching of what's called scalar parameters for Y. This is the space of sort of deformations of Y as a symplectic algebraic variety. These scalar parameters, the space of deformations, matches equivariant parameters for the dual guy. And this is, you could say more formally, what does equivariant parameters means? It means you have this big torus T shriek acting on Y shriek, and you just are picking a C star inside of this T shriek. So in fact, it's known that this space of deformations is controlled by the second cohomology of Y. So this ends up being an isomorphism between the second cohomology of Y and this the algebra of this torus. This turns out to be one of the easiest ways to sort of find symplectic dual pairs. Any questions about this notion of symplectic duality? I'm going to give a couple more, some more examples of.
This last point, you said that the torus can only be half dimensional at most, is that right?
Sorry?
The torus actually can only be half dimensional.
Can be as most have.
Okay. So if you've got a Y and you want to think about the dual Y shriek, this gives you some information about the dimension of that Y shriek. I guess.
Yeah, in general, it's sort of maybe hard to predict the dimension of Y shriek from the dimension of Y. It gives you a bit of information. Yes. Just trying to think if there's a better way of finding the dimension of Y shriek from Y. Yeah, I don't actually know how. I don't know any other way. You're right. That's a bit maybe as good as it gets. Okay, here are some examples. So I said this cotangent bundle of Pn minus 1. So these are dual pairs. And the cotangent bundle of Pn minus 1 is dual to C2 minus Z minus N. And actually, these two are both examples of this hypertoric varieties. So more generally, if you have a hypertoric variety, it's dual to another hypertoric variety, which can be obtained from the first one just by a purely combinatorial procedure called Gale duality. So for hypertoric varieties, is a very nice way to go back and forth purely combinatorial. For quiver varieties, which I mentioned briefly, but not in very much detail earlier, but I'll try to get back to them in a minute. Their duals are called affine Grassmannian lists. They're kind of my main subject of interest. And this duality was really one of the main motivations for this whole business of symplectic duality, because it helped. People knew that these two things were kind of linked, and that they both can be used to give a geometric realization in certain representations. But people didn't understand what the relation between them was until we put it in this framework of symplectic duality.
I'm sorry. Is the symplectic dual unique? I was wondering.
It's a good question. I mean, I don't. I mean, it seems to be unique. Let's say. So. Yeah. Yes, in a sense. I mean, there's some slight caveats, which is basically it's unique. Yes. And another thing which I didn't say is that it's an involutive operation. So if like if you take the symplectic dual of Y of the Y shriek, you'll get back Y.
Okay.
But again, it's not like I don't have a formal theorem about this. Just what we observe in examples.
Okay, thank you.
In the identification, in the symplectic duality in terms of cohomology, it's cohomology as a whole, but if you look at in terms of degree, is there a precise statement of what happened give a certain degree for Y in terms of the Y shriek?
It's a good question. It doesn't have a good answer because I lied a little bit. Yeah. I mean, one way to see that I might have lied is that on the right-hand side, there was no obvious gradient on the right-hand side. Because I lied, there's no way to answer your question. But maybe there's a sort of different answer, which involves this. Let's say involves this Hikita convection. But for this. Any other questions? Okay, so let me, well, I have a few minutes, not very many. I guess I'll try to explain a little bit about this quiver varieties and symplectic duals. It's like my main thing. Let me explain a bit more about the quiver varieties. So I explained before that if you have G, N, this is some group, which is some product. You think of it as like some product of some GLNs and some representation, then we can produce this one thing which might be a symplectic resolution. So we take the cotangent bundle and take this Hamiltonian reduction by G. In fact, the physicists tell us, like going back 20 years or whatever, that this G and N produces what's called 3D gauge theory. Some 3D supersymmetric monofield theory. And this 3D gauge theory has what they call two spaces associated to it. One space is called the Higgs branch. And the other space is called the Coulomb branch. And on the physics level, this business about symplectic duality is that this Higgs branch and Coulomb branch are the two spaces which are symplectic dual. So what are these two spaces? This Higgs branch is, by, I don't know, by definition or whatever, theorem or something, is this Hamiltonian reduction. And this Coulomb branch, the physicists had some ways of thinking about it, but there was no precise definition of this Coulomb branch until recently. So recently means 5 years ago. So the work of Bauerman and Nakajima, they gave a precise definition, mathematical definition of this Coulomb branch. So the definition looks a little strange right now, but it's a well-defined thing. So it's defined as spec of some algebra. So, and that algebra is a homology of some space. And that space is a space of maps from a funny curve, the union of funny algebraic curve, which is the union of two disks along a punctured disk called the Raviolo curve, to the stack quotient of n over 2. So it's a big mouthful, and even if I were to write, you could write this in a less compact way, it would be even more mouthful. This is as compact as I can write it. So a slightly crazy definition, and this is the definition of this Coulomb branch. So let's go to this quiver situation now. So what does quiver situation mean? So I start with a directed graph. So this quiver. So my graph is going to be very simple. My example graph. So I'll just take 3 vertices and 2 edges. That's my quiver. And then I choose that 2 what's called dimension vectors. So what I do is I choose two numbers for each of these vertices. So one set of numbers I'll put in circles, the other set of numbers I'll put inside of squares. These are just numbers. Positive integers. Or not. And then I put arrows. So this first set of arrows just goes according to the quiver, and the second set of arrows goes from those squares to the circles. And then the group I'm going to use is the product of the general linear groups of these circle guys. And the representation that I use is associated to all these edges. So linear maps associated to all these edges. So like some all edges, both from these guys, and then also between the squares and the circles. These squares are called the framing vertices. Actually, for some reason, let me just change the direction. So one example could be if we take the following. We take a quiver where I just have, say, n-1 vertices, and I put dimensions 1, 2, and so on at n-1, and then I put one framing which has an n. And then so this G and N, and then I produce this Higgs branch. So I take the cotangent bundle of N, and I take the Hamiltonian reduction of G. And if I do it in this case, this actually recovers the cotangent bundle of the flat gradient. So this is a general construction of Yasuda Nakajima from 30 years ago now, and it's very popular in representation here. Right? And what's remarkable though is that if we apply the Coulomb branch construction to the same G and N, I take this G and this N, but instead of doing Higgs branch construction, I do Coulomb branch construction, this Bowman, Finkelberg, Nakajima, complicated description. So then we obtain the following. So I guess this is their theorem. Coulomb branch. Gauge theory. So quiver gauge theory just means G and an M that are defined like that. Is an affine Grassmannian slice. So I guess I don't have time to define what this affine Grassmannian slice is. So it's hard to appreciate the theorem because I only told you one side of the theorem. But this affine Grassmannian slice is some certain space of that's already of great interest in representation theory. So it's kind of impressive that it comes as this Coulomb branch. And so one thing that's interesting about this one thing we're working on is that this a priori these affine Grassmannian slices are only really defined when this quiver is a Dickin diagram of a type ADE Lie algebra. But this allows us to define affine Grassmannian slices associated to arbitrary symmetric Kac-Moody groups. So that's one thing they're working on is studying these affine Grassmannian slices for Kac-Moody groups this way. Okay, I'll stop there.
Other questions?
I have a question. In the case, the physicist case, the Higgs and Coulomb, is the involutivity proven or
I don't know about proven, but
explained or?
from the physics viewpoint, there's for every one of these theories, and it doesn't have to be a gauge theory, it could be any 3D supersymmetric field theory. There's a dual theory whose Higgs and Coulomb branches are the opposite of the ones for the original theory. And also the dual of the dual theory is the original theory. So the involutivity there for them comes from the involutivity of this reality of these 3D theories. But I don't know enough about it to say whether that's a better argument than anything else.
But even in this quiver case, is it clear?
So in this quiver case, separately, these, well, in the case when this quiver is of type A, or affine type A maybe, then this involutivity is sort of clear. I mean, clear is a slight exaggeration, but it follows from this. One way to see it geometrically is using this bow variety stuff. And what's so-called Hanani-Witten transitions for bow varieties. Or you could view it as a fact that these affine Grassmannian slices are themselves isomorphic to quiver varieties, again in this type A, using this work of Mirkovich-Viborg. So I would say it's known, at least in the type A situation, but not in a very obvious way.
Yeah.
And if it's not of type A, then it's hard to say I mean, you can't sort of feed it back into the same machine. So there's nothing to check about the involutivity. You just have to take it out.
Could you say more about what you mean by affine Grassmannian slices?
I can say a lot more, but okay, here we go.
That's not what I'm asking. I'm asking you to see a little.
tell me the number of minutes you want me to speak for. Well, let me give it like terse definition, which can be appreciated by everyone. So let's say we have a group of G. So we're a semi-simple group. For example, like SLN or something. And it's the group whose Dickin diagram is that Dickin diagram. That's its relation to the quiver. So it's not the G of the, it's not this G, it's like the G who's related to this Dickin diagram. And then, well, this W and this V, they can be used to define a dominant space. And then this affine Grassmannian slice, well, here's a terse definition. We can say it's the space of pairs P, where P is a principal G bundle on P1. P is an isotrivialization away from 0. And where does this lambda and mu come into it? The poles of phi, so phi typically has poles at 0. This few trivial bundle. So it has some poles, and the poles are controlled by lambda. And the isomorphism type is given by mu. And there's some conditioning. So that's a kind of terse definition of the affine Grassmannian slice. Another definition, it's obtained by intersecting spherical Schubert varieties with the opposite finite codimensional cells. So, yeah.
So under this duality, is it possible to have something that's self-dual?
Oh, yeah, I probably should have mentioned it a long time ago. In fact, it's sort of on the, oh no, it's not gonna work, but yeah, this cotangent bundle, the flag variety is self-dual. What I started with. Well, you can see that a tiny bit here. If you put n equals 2 here, cotangent P1, and I already said this was also cotangent P1, and then it's 2. And in general, the cotangent bundle of the flag variety is self-dual. And there's a nice combinatorics here that the strata here are governed by partitions of n because they're orbits, they're nilpotent orbits. So in other words, Jordan types of matrices, Jordan types of nilpotent. And Jordan types is the same as partitions of n. And so in this case, it's self-dual, but there's sort of like a little bit non-trivial combinatorics going on here because it matches the components of the fibers with which are called Springer fibers with these attracting sets, which in this case are called orbital varieties. Both are related to this standard Young tableau through this partition.
If you have something that's self-dual, like a quiver variety that's self-dual, do you have a corresponding quiver? Like,
So
is it just the same quiver on each side, or could it be like there's a different quiver that gives rise to the same thing?
well, if it's self-dual, I guess it'll be the same quiver on each side. There's very few examples of self-dual.
Do we know if it's all the subduals that we have, or it's just that these are the only ones that we know?
It's a good question. It's the only one I know off the top of my head, but I wouldn't guarantee it's the only one. One related question is, I've given like many examples of symplectic resolutions this talk. You might ask, are these all the symplectic resolutions there are? And well, I certainly didn't try to give an exhaustive list, so it's certainly not all of them, but it appears that there's not very many more, and at least people don't seem to study any others besides basically a few isolated examples other than the ones that I talked about. So you might say that's a good thing, that it's some structure that's very rigid, or you might say it's a bad thing, because there's not very many of them around. Algebraists like rigid kind of structures.
For your W lambda mu, is there a stability condition?
No, because we have this this thing with the trivialization away from 0. So
Ah,
I think it's no need for this.
okay.
So in all these examples, is there, so you mentioned hyperkähler at the beginning, so there's a hyperkähler metric
In all these-
that comes naturally
Um,
attached to the space.
There is in the examples, but it's not. And in general, I would say it's conjectured. But for example, in this construction of Robin Finkelberg Nakajima, it's not known in general how to define a hyperkähler metric, but it's believed it should exist. For these Affine Grassmannian slices, yes, there's a hyperkähler metric. For these varieties, yes. Hypertonic varieties, yes.
Okay. There are no extra question. Let's thank the speaker.